In this video, we'll continue by discussing the central limit theorem and how it impacts our use of the normal distribution and informs the practical applications to which we can apply. Recall that for a random variable, we can always draw a sample mean and a sample variance or standard deviation for data. So if we sample a bunch of different individuals, we could calculate their mean, assume that we randomly selected 30 students from the university, calculated their mean GPA, and consider that if we again took a random sample and again calculated their mean GPA, that second sample's mean GPA isn't going to quite be the same as the first one. And I mean, thinking about this, it's actually almost impossible to get the exact same sample from a study. Also, it's impossible to get all of the different samples. We can't just go out and collect the millions and millions and millions of different samples, all possible combinations of students. Be an interesting combinations problem. But we couldn't calculate all of those possible samples and find their mean GPA. So what we do is we consider each of the individual people's values and the mean of the individuals' values and their standard deviations, and then we calculate a distribution regarding the means of those samples. So the sampling distribution is a distribution for the means. So this is very, very, very tricky, so please pay attention closely to this. Our original distribution, the continuous, the normal, whatever we were talking about, that distribution was a distribution of raw data. So a distribution of the GPAs of students at the university. In this case, the sampling distribution is a distribution of the means of different samples of students. So let's say we took samples of 30 students from the university, calculated their mean GPA, took another 30 students from the university, calculated their mean GPA. If we looked at the first mean as a single data point, the second mean as a single data point, the sampling distribution is, if we continued on, the distribution of all of those sample means. So our initial distribution was of the raw data. Now we're talking about a distribution if we took a sample and took its mean, took a sample, took its mean, took a sample, took its mean, took a sample, took its mean. All of those means make up this different distribution called a sampling distribution. And there's a really cool image on page 255 in your text. I highly suggest checking it out. I think it's pretty handy. So if we select these samples with replacement, then the sample means are going to be a little bit different from the population mean, right? And again, we mentioned earlier, no two samples are going to have the same mean. The difference between each of the sampling means and its population is called the sampling error. And that just means that each sample isn't perfect. It doesn't perfectly represent the whole population. Now, this distribution of sample means is actually really important. We're going to talk about this in a second. And that is, again, not the raw distribution, but the distribution of the means of samples of a specific size. So first of all, there's some properties that are handy. The distribution of sample means, the mean of the sample means. So if I have the mean of the first sample, the mean of the second sample, the mean of the third sample as my 3 data points, the mean of those 3 data points is the same as the overall population mean of the raw data. So pause, think about that for a second. The mean of those means from each of the 3 samples, if we kept doing that for all of the samples, the mean of the means for all the samples is going to be the same as the population mean. Now, an interesting thing to think about here is that the standard deviation is going to change a little bit. Now, the notation is important here, so please take a second to look at this notation. Sigma is the standard deviation of the raw data distribution. That's our original standard deviation we calculated earlier. Now, if we're looking for the standard deviation of the sampling distribution, the standard deviation of the mean, we'll call that standard deviation sigma sub, that's just under it, x bar. So this stands for standard deviation of the sample mean. And remember, x bar is the sample mean. That is the standard deviation of our raw data divided by the square root of n. So the standard deviation of sample means is called the standard error of the mean, and this is an extremely important concept. So when you hear me say the standard error of the mean, all I'm saying is the standard deviation of all of those different sample means. So again, this is, we took a sample, we calculated its mean, we took a sample, we calculated its mean, we took a sample, we calculated its mean. The distribution of all of those means has a standard deviation of the standard deviation of the raw data divided by the square root of whatever sample size is being taken in all those samples. All right, now that's a lot, but that leads us to what the central limit theorem is. If we're looking at the distribution of means, and we're looking at a reasonable sample size, 30's a ballpark, you'll hear 30, 50, 30 and 50 are the two main ones you'll hear. We'll use 30 in this class. The distribution of means is normal. And it doesn't matter what the original raw data looks like. Now, this is a huge, huge piece in statistics, so let me say this one more time. If we look at the raw data, and the raw data is some utterly bizarre distribution, just think about drawing a huge squiggle, so it doesn't look at all like that bell shape. But if we took 30 people from that distribution squiggle and calculated their mean, and then another 30 and calculated their mean, and then another 30 and calculated their mean, and then we plotted those means, we made a distribution of those means, no matter what the original raw data distribution are going to have a normal distribution. And this is very cool. This is why we spend so much time working with the normal distribution. More than just having a normal distribution, they're going to have a normal distribution whose mean is the mean of that whole raw data set. So if you know the mean of the raw data, you know the mean of that normal distribution of the sampling distribution. And they're going to have a standard deviation that we drew on the previous slide. That is sigma divided by the square root of n. So if I'm taking a sample of 30 for each of my samples, that n is going to be 30. Drawing this out, the distribution of the sample means, as long as the sample is greater than or equal to 30, is going to be normal with a mean of the original data mean and a standard deviation of the raw data divided by the square root of n. Now this is really, really, really interesting, because if our sample size is sufficiently large, that is greater than 30, we can use the normal distribution to talk about sample means. That is, what do we think about the mean of the sample? In the same way that we were originally talking about individual values, it's not written on here, but a big thing to note is, but now we don't have to care about the original distribution. If we're looking at the mean of a sample, I don't have to care about the distribution that the original sample came from. Actually, as a professional statistician, this is an extraordinarily important concept. If my groups are of a sufficient size, I don't care what the distribution of the raw data is. The distribution of the mean is a normal distribution, and everything that we've done thus far in this chapter will now apply. Now we're going to have to edit our z transformation a little bit, because that transformation we were doing originally was for an individual value. Remember, we had x minus mu divided by sigma. But now our x value is that sample mean. So we're going from an individual value, which was x, to a sample mean, which we call x bar from our previous chapters. And now, remember, the standard deviation was sigma. Now we're looking at the standard deviation of the sample means. That's called the standard error of the mean, and that is sigma divided by the square root of n. So now this is being written in terms of the mean instead of an individual value. So we'll use this formula when we're talking about samples and looking at the distribution of their means, we'll use the previous formula when we're talking about individuals and looking at individual differences. So let's get started on a couple examples to help you understand. So we have children between 2 and 5 watching 25 hours of TV. So we've got a normally distributed variable, standard deviation 3 hours. If 20 children are randomly selected, find the probability that the mean is greater than 26.3. So the biggest thing that I'm looking at here is that I'm looking at the mean number. I'm no longer looking previously, if we wanted to ask this question in the previous way, we would say if a child is randomly selected, what's the probability that the number of hours they watch is 26.3? So that's the previous version about individuals. But now we're asking if 20 children are selected, what's the probability that their mean number of hours is greater than 26.3? So this is telling me that instead of using my old single values Z transformation, now I'm going to use my new central limit theorem version about the sampling means. So we're going to transform this into a standard normal. Again, we know this is normal. Now, I say somewhere in here, assume the variable's normally distributed. That's because our sample size isn't quite big enough. Note that if our sample size was like 30 or 40 or 50, I wouldn't even need this statement. This could be any distribution in the world. It could be a distribution you've never even heard of. So we get to remove this statement. Now, this is a small thing in terms of a class problem, right? In a class problem, I just remove like 6 words and it's gone. But in the real world, this assumption is critical in the ability to say, I don't actually have to know, I don't have to assume that the number of patients who visit an emergency room is normally distributed. I don't have to assume that the number of defects in a computer is normally distributed or whatever. To remove that assumption makes this applicable to virtually every problem we run into. So anytime you run into a data set, if you're looking at a mean of a sample, if that sample is big enough, you can apply what we're doing for any continuous data set. It doesn't matter where the data came from. And that's the cool part about this, is you can remove this assumption. Again, a small thing in an in-class problem, but a huge thing in the real world. All right, so continuing on with this problem, again, this distribution is going to have a normal distribution. We know because of our central limit theorem if this were 30 or bigger, and because it says normal. Now the raw data has a standard deviation of 3 hours and a mean of 25 hours. Our new data set we're going to have to take into account and think this through. But first we're going to transform this into a standard normal. So we're going to transform this 26.3 and the normal distribution that comes from into something that we can look up on our table. So we're going to use our new formula, again, because we're talking about a sample and the mean of a sample and the distribution of a mean of a sample. We're going to plug in x bar, that's the mean that we're interested in this problem, that's 26.3. Mu, that's the mean of our raw data, that's 25. Sigma, that's the standard deviation of our raw data, that's 3, and little n, that's the sample size, that's going to be 20. So if you're not following this, pause, try to track where these numbers are coming from, maybe go back and see where I'm pulling each of these numbers come from, rewind a little bit, but make sure you're tracking where each of the numbers are coming from for this. We'll have another example coming up here soon too. Plugging all of this in, I literally type this into my calculator. Be careful of your parentheses here. It might be worth doing the denominator separately and then doing this whole division problem. I end up with 1.9379 as my z-score. Now I'm looking for greater than this. So drawing out my table, and this is a bit elementary at this point in the course, but you can always do it whenever you need just that little mental bump of what you're doing. Drawing out my normal distribution, I have a z-score of 1.9379. And I want to find the area above. Now remember, my table only finds the area below, but I just do 1 minus the area below to find the area above. So my table 2, my z-score only goes out to 2 decimal places, we'll make this 1.94. Then we'll go on the table down below, look for my z-score of 1.94. These are my negative z-scores. I'll go down to my positive z-scores. So I'm looking at 1.9 and then 0.04. And so I'm going to track these all the way in. 1.904 leaves me with 0.9738. So this is, again, the area to the left. Don't get confused. It's a common place to miss points on the test. 0.9738, I think. So this is my area on the left. That means that my area on the right is 1 minus 0.9738. So that's going to be 0.0262. So about 2.6% of individuals exhibit this trait in this case. For these samples, if 20 children are randomly selected, the probability that the mean number of hours is greater than 26.3 hours is about 2.6%. So there's only a 2% chance that their mean is going to be bigger than 26 hours. All right, go on and pause and give this one a shot on your own. Meat consumption of a person per year. All right, so working this through, find the probability that a person, so did you catch this? This is a single individual. This is a single individual. So if you didn't catch this, think about which equation you use for a single individual. Pause it, retry this problem for a single individual. All right, so for a single individual, we've got the value minus the mean divided by the standard deviation. This is our old equation. Remember, our new one would be something like find the probability that for a sample of 20 people, that all the mean of the 20 people, that the mean of the 20 people is less than 224 pounds per year. In this case, I'm looking for a single individual. I take the value that we're interested in, subtract the mean, 218.4 of the population, divide by the standard deviation, and that equals 0.224. Incidentally, for those of you who are getting this, and this is pretty easy, think about that if you had a single individual and made your sample size 1, this all works out to be fine even if you use the other equation. Looking up this probability in the table, I find that it's just the straight lookup one because it's on the left. So in the table we've got 5871, so about 59%. So in this case, the probability that a person consumes less than 225 pounds of meat per year is about 59% according to this data set. And again, this is the old way that we would do this, not because it's any less useful, but because we're looking at a person. We're looking at the probability that a person consumes less, not that the mean of a group of people. So let's look at this again under the new way. So assume that a standard deviation, these are all the same numbers. Now we're looking at a sample of individuals. Okay, this is a good sign. And now we're looking at the probability that the mean of the sample will be less than 224. This is a big difference. This is a big difference. One other way that you can look at this is if you need n, if you need the sample size, well, that's going to be your new way. If you don't have a sample size, you don't have a sample at all, that's going to be the old way. That's going to be the way that we used to do it. So go on and pause right now and give a shot to this problem. All right, working through this. We start by transforming it into a standard normal. We use this equation. Remember that our sample mean, this is what we're interested in, 224 pounds. This is the mean of the sample that we're interested in, being less than. The overall population mean, this is the average number of pounds overall, is 218.4. That's our mu. Sigma, that's our standard deviation. This says assumed standard deviation is 25 pounds. And then n, the sample size, this is what separates this equation from the other one. The other one didn't have the square root of n in it. The square root of n is our 40 individuals. So 40 is the n, so we're going to be taking the square root of 40. Plugging this into my calculator, I get a very different z value than I got earlier. And looking this up on the z table, I find that the area below is 0.92222. So there's about a 92% chance that if you took a sample of 40 individuals, the mean is going to be below 224. Again, a very different percentage. Go on and pause and give this one a shot. Think through what's going on here. Is this a sample? Is this a mean? Make sure you're doing the right equation. Note that this one is a two-sided one, so it's going to be a little harder, but I think you can do it. Give it a shot. All right, so first we're going to take this. This is a sample, and we're looking at the probability of the mean of this sample, so we're going to be using our new equations. Now we're looking in between two values. So we've got two values of interest here. We're going to calculate two z-scores for each of the values. So the first one is this 1.5 z-score. We plug in our numbers for the first value, 100 minus the 96 overall average, divided by 16. That's the standard deviation for the population, then divided by the square root of n. In this case, our sample is 36 vehicles. Then we're going to be looking at this second value, 90 months, and calculating a second z-score for that. Now remember how we approach this. We approach this by finding the area to the left of the bigger one, then subtracting out the area to the left of the smaller one to see how much area is left in between. So in this case, the area for the bigger one is 0.9332. The area for the smaller one is 0.0122, and subtracting the two, we get our final answer of 0.9210. So the probability that our mean of this sample is between 90 and 100 months is about 92%. I'll say that one more time. The probability that the mean age of a sample of 36 vehicles that are randomly selected from this population, the probability that it's between 90 and 100 months is about 92%. It's about a 92% chance that that mean of a 36 vehicle sample is in that range. So one thing that is important to mention here that we don't talk about often, but you're not going to really see anywhere else, is the finite population correction factor. And that's saying that whenever we're dealing with a population that isn't infinite in size, so normally when we approach statistics, we think that populations are very, very big, infinitely sized. But when this isn't true, we have to alter the standard error calculation. So the standard error calculation needs this new component in front of it, this square root of the capital N minus little n divided by capital N minus 1. Now remember from that little notes in the back of your notebook that capital N is the population size, little n is the sample size. So in this case, we're doing the population size minus the sample size divided by the population size minus 1. This square root at the beginning is used to correct this, and in fact, that term is called the finite population correction factor. It's the part of the equation that corrects for the fact that the population may not be infinitely sized. So if n is infinity, this kind of all goes away and we just have what we normally have. But when n is not infinity, let's say you've only got, 30,000 students at your university. So capital N might be 30,000. That's the total number that you could use. Then you would want to use this finite population correction factor when you're calculating your standard error of the mean. Because of this, our z-score is going to look very similar, but in the denominator, instead of having our old standard error, which is sigma divided by the square root of n, you're going to have now the whole finite population correction factor standard error, which is this whole kit and caboodle. So the larger populations get, the less this matters. In fact, this is kind of just a side note just for your own information if you're ever working through this. It's something that's not particularly often mentioned in statistics, but frankly, we do reasonably often have limited population sizes, and these finite population correction factors can be very important when looking at data from a finite population. So this has finished our discussion of the central limit theorem and how we apply this in applied situations. Next, we're going to talk about the normal approximation for the binomial distribution and how that can ease some of our calculations that can be complex or tedious when we have to do it by hand.